Okay, so today we're just going to discuss the applications of the functional calculus that we saw. Namely, today we're going to discuss path integral in quantum mechanics and in quantum field theory. So this is called path integrals. So the motivation goes something like this. I think Saif asked this question in the very first class in classical mechanics, or in, so to say, classical physics. You want to go from point A to point B, and there are many choices for the path, right? And what does the principle of least action tell you? That the particle will go in such a path that the action is extremized, right? So let's say this is your correct path. That means among all these paths, there will be only one path that is correct, or so to say, physical. The difference between the path integral and the principle of least action is something like this. So this is your classical picture, and this is the quantum picture. Similarly, you have this A and B. You have a particle that can go from A to B in different, paths and stuff like that. But since quantum mechanics or quantum field theory, whatever you want to call it, this is a theory of probabilities, right? So each of these paths carry a certain probability. Let's say this carries 1 upon third or something like that. This carries some 4 by 5 or whatever, some number that is less than 1, between 0 to 1. Yeah. So all these paths are, viable for a particle. A particle can take all these paths to go from A to B. And in path integrals, what we do is that we sum over all of these paths. So that's your difference with the classical picture. Okay. In quantum physics, or the quantum picture, you are taking into account contribution coming from all the possible paths between A and B. But in the classical picture, there is only one path for which the action is extremized. So this is the difference between your classical and quantum picture. And let's now dive into path integrals in quantum mechanics. And in due time, we'll try to give a clear meaning to what does this path integral truly means. Okay. So path integral in quantum mechanics. And we'll deal with a single particle for now. Single particle quantum mechanics. Okay. So if you know some quantum mechanics, you know that the center point or the punchline of a quantum mechanics is, oh, you have a particle, then you should be able to define some Hamiltonian for it, right? So for a single particle, the Hamiltonian would look something like this. Some P of Q. Again, this H, P, V, they are operators. If you are confused, you can put a hat over them. But usually we don't. It should be clear from the context that you're dealing with. In fact, this Q over here is also an operator. And the Schrodinger equation, as you already know, something like this. Right? And the formal solution of Schrodinger equation let's call this equation 1 instead of writing Schrodinger. Time t t naught, right? I hope everyone knows about these basics, right?
Where the exponential is like a unitary matrix, right? Or unitary operator.
Yeah, this is a unitary operator, exactly. And the unitarity is necessary because of the probability conservation. Okay, so what we want to do is that we want to take an alternative route to the canonical quantization. Okay, the canonical quantization is the quantization where you first promote the variables to operators, and then you find some commutation relation between them, and then you proceed to quantize. Instead of doing that, what we will do is that we will deal with a non-operator Hamiltonian. By non-operator, these are not matrices, or the operators that you see in your quantum mechanics. Rather, this will be just the ordinary Hamiltonian, something like this. And what path integral does is that, let's say this is your path integral. It takes in the classical variables and it will output some operator result from standard uh, operator quantum mechanics. We'll see how this is done. This is what path integral does. But for now, let's start with the thing that we call a transition amplitude. This will be a quantity of interest when you deal with the path integral stuff. So transition amplitude. Let's say you have some state like this. This is an abstract state of some particle, and after some time, let's say it goes into a state like this, x prime t prime. The transition amplitude is given by the inner product of these two states. Okay. Okay, I think I'm out of pages, so I'll have to add some pages as well. So these are your transition amplitudes. Now,
I have a question. Maybe you have to put a T prime over here. Is it right? X prime
sorry.
T prime, X prime T prime.
Oh,
প্রথম
the two
expression.
prime
Yeah.
notations. Okay. So, okay. So this is your transition amplitude. Keep this in mind. You will see this in a few moments. So, how do you write a wave function in quantum mechanics? The way to write a wave function would be something like this, in the position representation. Because you will see all these t's over here, because if you know already, time is just a parameter in quantum mechanics. So these abstract vectors, this size, they will have this time inherited with them. Time is just running on the background. So this is how you write your position state or position representation, whatever you want to call it. This is also known as the wave function of a particle. Now, what happens after you apply the Hamiltonian? That means if there is a Hamiltonian, it does what? Can anyone tell me? Like just
Changes the
from the,
state.
okay, why is that? Why should
Uh,
you change the state?
that's what the Schrodinger equation reads.
Okay, good. So if a Hamiltonian is changing your state, you are writing this final state as this e to the power I h t t0, something like this, right? Now you can show that uh, using the definition of the wave function, the position representation of this final state will be something like this. Let's say q q I h t psi of t0 equals to some psi of qt, right?
Yeah.
So let's do something with this guy in the box, that we are writing it like this. Okay, so psi of qt is equals to, again I'm writing it down. Now are you familiar with this expression? This is a completeness relation, or so to say, the complete set of bases when your q is a continuous variable. This is called the completeness relation. I think if you have done math 2 or 3 or linear algebra in any sort of with the bracket notation, for a finite dimensional case, these are your you interpret them as basis vectors, and for any basis vector, only one entry is 1, the other entries are 0, and if you sum over a product like this, which is an outer product, if you sum over all the bases, you get an identity matrix, right? Okay, so even if you don't remember, don't worry about it. Accept this for now. Maybe I'll just put one in your exercise sheet. So what we can do right now is that we can invoke this completeness relation inside this equation over here. So let's do that first and see what happens. So what we want to do first, we want to take some integral measure. There will be this q e to the power I h t. There is this q naught psi of, instead of t0 I can write as 0 just to make my life a little bit easier, right? I can write this. Okay, so if I write this in the next line, what I can do is that I can write this measure again, this guy q0, and this is what, this is just the wave function for the particle at position q0 on a time t equals to 0, right?
So we're saying that there's an identity around the E or around the unitary matrix, and
Well,
we're just saying
we can
like what
always
we're looking
write,
for.
yeah, we can always do this. Let's say this is some operator, right?
Mm-hmm.
You can always invoke the identity over here,
Yeah.
because this is just identity, right?
Mm-hmm.
That's why we invoked it. Now before I go on, what we did over here is that we took the definition of the wave function and turned this expression into an integral equation. So this expression over here is actually an integral expression or an integral equation. You don't have to worry about integral equations, it's just a name. In some case it's useful, but for now it's just,
Uh,
I'm just telling
why
it
did you
for you.
choose the notation Q naught? Does it have anything to do with the
It's
initial value?
well, you can think of it like that, yeah. No, not the initial value.
Acha. I
Let's
mean,
say
like you
you're
could have chosen another index like Q prime.
like, okay, so you're going from, let's say, q not to q. Okay, so by initial value, I think what you're trying to say is that, okay, maybe I started from this q on the position space. You get what I'm trying to do? The idea of path integral is that you want to go from here to here, right? And the idea, what I'm going to show you right now, is that instead of taking a continuous path, just make it into a lot of discrete paths with very small intervals. Okay, it doesn't have anything to do with the initial value. Rather, what you can interpret is that, okay, maybe it's some initial point or a reference point, and you are trying to go from q naught to q. Okay, is that clear?
এখানে কি অপারেটর চেঞ্জ হইতেছে লাইক অপারেটরটা কি টাইম ডিপেন্ডেন্ট বা এরকম কিছু
Why would your Hamiltonian be time dependent? Would you be in the
না না
Schrodinger?
না ওই হ্যামিল্টনিয়ান না ওই যে কিউ অপারেটরটা মানে পজিশনে লাইক একটা তো
Why is
আইগেন
why is q a, why would q is a like, these are complete set of basis vectors, right? This is not an operator, no. Like the q's individually, yeah, they're not operator, they're just your position basis vectors, and when you sum over all of them, then you get the identity operation.
Acha.
Okay. And no, we are not dealing with any sort of Hamiltonian that is time dependent. If you are asking whether the Q operator inside the Hamiltonian is time dependent, no, we are not doing that. If you want to do that, you will have to use some Kac-Moody algebra and stuff to derive this thing that we are trying to do right now. Okay, so yeah, okay, so let's move on forward. Again, what I'm going to do is that I'm going to invoke another identity. So say dq, let's say this is dq1 q iht, and then again what I'm going to do, I'm going to just invoke another identity. Let's say q1 q1 q0, stuff like this, and I can go on and do that forever. But the punchline here is that when you invoke this identity operation over here on this line, you can rewrite this equation as follows: dq0, since this is an integral equation, it will have a kernel, and the kernel is coming in terms of what? q0, q, and t, right? And you have this q0, 0. Now there is something special about this kernel. You can see there is some time, right? E to the power I h. Please speak. Feel
Kernel
free to
ki
speak.
Janish.
If these are just okay, so are you familiar with integral equations?
Na.
Okay, so then this is just something. Okay, just ignore that. Kernel is something that comes in an integral equation. You take some function, the kernel acts on it, then you integrate it, then you get the resulting function. That's what you are seeing from this equation, right? Yeah, so the knowledge of integral equations are not necessary. I'm just telling you for your information. If you're interested, you can look that up. Okay, so this k is called a kernel, and what we can do right now is that we can draw something that how to say this. In the x-axis, let's say we are plotting our time. On the y-axis, we are plotting our positions, and our goal is to go from this q0 to some place called q, like this. And there are many ways you can go. For example, let's say this is one of the paths. Okay, and since this is a time axis, let's say the final time is t, and here it's 0. So from 0 to t, the particle goes from q0 to q. And what you can do right now is that you can break this path into very small steps. Let's say this is t1, t2, t3, so on. Who needs a permission to join this meeting? I added everyone in the calendar. So what you can do right now is that you take your quantity in the kernel, that is the main quantity of interest between this q0 and q, e to the power I h t, and break the total time interval into smaller time intervals. What I mean by that is something like this. Take your kernel q, q0, t. Okay, no, let me just show it in a more easier manner so that you can understand. First, take this exponential I h t. Okay, and note that these are not the same thing. This is just t, smaller t, some intermediate time, and this is the evolution operator at its finest. By finest, I mean at this point. Okay, So this guy counts from 0 to t. So if you do t minus 0, this is just capital T. And you can break this up by following: exp negative I h some n plus 1 step minus n step times exp negative I h tn minus 1, and you can go up to exp of negative I h t of 1. And after this breakdown, you can put this quantity over there. That means instead of this, you can just break this up into more smaller segments or something like that, whatever you want to call it. So if you do that, your kernel, the k thing, would look something like this. Again, this is a product symbol. It means you are multiplying the stuff. Tq of r, q of r plus 1, exponential of I h, t of r plus 1 minus t of r, q of r. Okay. And notice the product symbol over there. So there are r equals to 1 to n, right? So in between, you just put different indices for r, and all of them are just multiplied with each other. They're stacked against each other. And then finally, the last quantity, q1 exp of negative I h t1 gives 0, like this. Okay. Is that okay, or is everyone confused right now? Like, how did you do this?
প্রোডাক্ট সিম্বল ইউজ করলে কি লাস্টের কি ওয়ানের এটা লেখার দরকার আছে?
This guy is
এটা তো
outside this
চলে
product.
আসবে।
No.
um,
Just match the indices, okay? Why r1 is there? If you put r equals to 1, then what does this quantity tell you? There is this q1 and this is q2. And why is this q1 like this? Is true, right? Identity. So when
yes.
you invoking for q1, there is one q1 there that is associated with q0, right? And there should be another q1 that should be associated with what? q2. So your product symbol is actually working on this guy only, not this guy. Okay. Okay, just write them inside separate brackets. Okay, so moving on. Now there is one thing. For our case, we are going to take the difference between these time intervals for all the r's to be same, but this doesn't have to be the case necessarily, but that would require a more rigorous derivation. If you are interested, you can consult Peskin. We have Peskin and Schroeder. I don't exactly remember the chapter number. Perhaps it's chapter 11. They do not assume that the interval between the time steps are equal, but you can do that, because at the end of the day, you are taking those intervals to be 0. I mean, the limit of those intervals, they go to 0, so you can do that. But if you want a more rigorous derivation, you may consult Peskin and Schroeder. So if you do that, that means you are considering on all the time intervals to be equal. That means for any r, you are saying that t of r plus 1 minus t r is some delta t. And for this guy t1, you can always think of it like this: t0, right? But what was t0? T0 was simply 0, right? So you can also write it like this as well. So let's do that and see. At this point, we're just manipulating the algebra. That's it. We're just doing math. Okay. So
I have a question.
yeah.
So, the big time operator, big T, is advancing the time by a long amount, but we're like basically dividing it into a little.
I couldn't hear the last part of your question properly. Like, are you asking, okay, is this big T means a very long time?
Not,
Something
I
like
mean,
that?
not a very long time, but like a macroscopic amount of time, and then we're separating it into a product of very small amounts of time.
We can always do that, right? Like, take the real number line, for example. This is 1, suppose, and this is 1 point, I don't know, 0.0000001, maybe. How many more numbers we can get between these 2 points?
Infinitely many.
Exactly. So we
Yeah.
can do that.
Oh, so that's what we're doing here, right?
Yeah. Whatever the time you are considering, like your state starts from some reference time. Okay. And you want to measure, okay, what is happening at after some time t. It really doesn't matter how much small that is, but theoretically you can always you know break those uh, break that long gap, or so to say, the short gap, into much smaller steps.
I see.
Theoretically we can do that. Okay. Okay, so let's move on. Where were we? I'm a bit confused right now. These things are very confusing. Okay, so we are manipulating the kernel. We wrote the time intervals as delta t, right? Okay, so let me write that again.
আচ্ছা, সো কার্নেলে বেসিক্যালি আমরা জাস্ট কিউ নটের সাপেক্ষে ইন্টিগ্রালটা নিই না, মানে এই তো বেসিক্যালি ডিফারেন্সটা, লাইক জাস্ট কার্নেলের ইয়েতে এক্সপ্রেশনটাতে, মানে
Yeah.
কার্নেলের এক্সপ্রেশনে তো আমরা কিউ নটের সাপেক্ষে ইন্টিগ্রেট করি নাই, লাইক ওটা হচ্ছে একদম ফাইনাল ওয়েভ ইকুয়েশনটার জন্য নাকি? আচ্ছা,
Yeah, just look at this expression. uh, Here the reference time was 0, and we said, after some time small t, my state goes from psi q naught, or psi naught, whatever, psi naught to psi, right? So first we have to determine the kernel, and the integration on this q naught, it won't act on the kernel itself, rather it will act on the kernel times the initial condition or initial wave function, whatever you want to say. Yeah. So on the kernel, when we are manipulating this one, there is no integration over dq0 or q0. You're right. Yeah. Okay, so let's try to write it down in a more productive way, so that this can be useful to us later. So if you do that, what do you think happens? They just get replaced by this delta t's, right? Nothing much. Now I'm going to show another point. That is, okay, we are done with these small time steps, determining the kernel and stuff, but there's still a elephant in the house, and that is this Hamiltonian itself, which is an operator. And now we have to deal with some products of operators and stuff. This doesn't seem very easy. So now I'm going to discuss something that will tell you how to deal with this kind of stuff. So first of all, note that the Hamiltonian is coming in terms of the operators p and q's, right? Because for a single particle Hamiltonian, we have this thing, v squared 2m plus v of q, with some well-defined potential and stuff. So the first thing that comes to your mind is that, hey, can we do something like this? Let's say I is squared by 2m plus v of q. There is this delta t, q of r, right? So you might be tempted to write this e to the power, let's say, minus p squared by 2m. There is this I that is multiplied with the whole thing times v of q as e to the power negative ip squared by 2m times e to the power negative I pq. You may want to write this, but you cannot do that because this p and this v are operators. And this is where the Baker-Campbell-Hausdorff formula comes to the rescue in some sense. Are you guys familiar with the BCH formula, the Baker-Campbell-Hausdorff formula?
Yes.
Okay, that's great. So we are going to take a little bit modified version of that. I think the formula goes, if I recall correctly, the formula goes something like this, right? E to the power a. So this is the BCH formula, Baker, Campbell, and Hausdorff formula. This formula goes something like this. This is e to the power a plus b plus 1/2 of the commutator of a and b. Or sometimes this part, the commutator part is written on the left hand side, but it really doesn't matter. So this is the BCH formula. And the only modification we need for our case is that we need to multiply these a and b's with some infinitesimal parameter. Why? Because look at this guy over here. This is some infinitesimal parameter. So we need a modified version of it. How we can do that? Well, let's try to write something like this. So this is the modified version, or the version that was suitable to our cause. You can think of it like this as well. So if you have this infinitesimal parameter, you can rewrite this thing as follows. Exp. Notice that this epsilon is a parameter, right? So it's what? A scalar, not an operator. So operators, how to say this? You can always multiply operators with what? Some scalars. That's the property of a vector space, if you recall from your linear algebra course. So you can write this as epsilon a plus epsilon b, right? Let's call this epsilon and epsilon b as a prime b prime. So b prime. Now you apply the BCH formula. So this is e to the power a prime, e to the power b prime. Oh, sorry, it should be plus b prime, e to the power minus 1/2 of commutator of a prime b prime, right? But now you can replace the initial thing that you started with, that is a prime is equals to epsilon a, b prime is equals to epsilon b, and you have epsilon a e to the power epsilon b, and there will be a e to the power minus 1/2 epsilon squared commutator of a and b, right? Is this okay with everybody? Does everyone understand this? How did I do this? Okay, good.
Yes.
And this is a very nice thing we do in physics. Anything that is order epsilon, where epsilon tends to 0, is negligible. So this guy goes to heaven. We are just simply ignoring this. Okay. I hope no
Meaning
one.
then the exponential would go to 1, right?
No, I mean not 0. We are just ignoring it. This is oh, what you're saying? Will that go to 1?
Yeah,
when you
because
take
e to the
epsilon?
0 equals 1.
Well, yeah, maybe if you want to say it like that. What I would like to say, the more formal way would be to expand this exponential.
Oh, right, yeah.
First term is actually the identity operator, and then you have this epsilon squared commutator of a and b, then you have epsilon to the power 4 commutator of a and b squared, and so on. So all this order of epsilon squared would go away. You should end up with an identity operator, because these are also operator expressions, right? That's a more formal way to do it. But what you said, I totally agree with you. Take epsilon to be 0, multiply with 0, e to the power 0 is 1, and all that. It's fine. We are physics
এখানে
people.
টেইলর এক্সপান্ড করা যাইতো না ওই যে ই টু দি
That's what
পাওয়ার
I said, right? That's what I said to Saif.
আচ্ছা
If you do the Taylor expansion, one thing you have to specify is that the first term is by definition the identity operator.
One identity.
Yeah. And what Saif was saying that, oh, let me take epsilon goes to 0. It's multiplying, you are multiplying two well-defined operators with 0. So that should give me another 0, you know. And then there is e to the power 0. Oh, that is just 1. Yeah, but ওইখানে আর একটু ফল্ট আছে, যদি কেউ চায় সেটা ধরতে পারবে আর কি, because even if you take epsilon to be 0 and this becomes 0 and a and b are matrices or something like that, all the entries of those matrices will be 0. So then you have a to the power of 0 matrix, which is by definition not 1. Nobody knows what that is. Yeah, okay, so this part is done. Let's not waste our time talking about this silly stuff. So what we have seen over here is that if we have some operators a and b with some infinitesimal parameters multiplied to them, we can detach them, right? So that's what we are gonna do on this expression over here. We can write so using this modified BCH, we can write q bar plus 1 e to the power negative I p squared by 2m e to the power negative I b of q. And please don't get confused, these are all operators, p, q, v, all operators, okay, for now. Q of r.
Did you miss a delta t on the exponential?
Oh yeah, I missed a delta t. Yeah, thank you. Now I'm going to do another thing that's probably gonna don't make any sense to you people, but I'll try my best to justify it. You all know that for the position operator q, let's give a hat so that nobody gets confused anymore. This is the eigenvalue relation, right?
Yeah.
Okay, good. So what I'm going to I'm going to give you an argument right now. For this expression, do you see any way that I can somehow pull one of these exponentials out as a scalar something? Like I don't want to deal with operators anymore. So
Right. You can because v of q can be written as a formal series of q.
exactly,
So,
not
yeah.
the formal series. Formal series, if I remember correctly, formal series, something that is not convergent. But yeah, from the physical point of view, any sort of well-defined potential, we can write it in terms of some polynomials, right?
Right.
Right. So let's say there is some e to the power some polynomials here. Let's say forget those I and delta t's and whatever there is. Let's say it's something like q plus q squared, where q and q primes are operators, right? And there is this q. They're acting on some position eigenvector. Okay. Now you can expand the exponential again, right? So the first term is the identity, and the second term would be q operator, q squared operator. The second term, the third term would be q hat, q squared hat whole square, and stuff like that. And they're gonna act on this position eigenbasis, right? So identity just leaves it unchanged. So this is like q, and then you have this q hat acting on q, q square hat acting on q. So what you have is something like, again, q, q of q. Again, these are scalars now through the eigenvalue equation. So q square q and ta ta ta. So ultimately what you have is something like this one. Where this guy is actually a scalar or a number, or so to say, some sort of an eigenvalue or something. Not the eigenvalue, but it's a scalar. And there is some implicit identity operator over there. So that's why I can pull out this quantity and write this expression over here as the following. e to the power negative I v of q. Now these are all scalars. They are not operators anymore. This v and q, both of them. V, why was v operator? Well, v is coming in terms of q, which was an operator. So v itself should be an operator. Okay, just in case you are confused. So
The delta t again.
oh, sorry. So you can write this guy. So somehow we dealt with the q things, right? Now we have to deal with these p operators or the momentum operators. So now I'm going to show you something that will come up as an exercise. You already know that on the position basis, this is your completeness relation, right? A similar
Yeah.
relation exists for the momentum basis, and that is given by this. Actually, this 2 pi, it's not that relevant. It totally depends on your convention. And this is just this. Okay, we're gonna use the second relation, and this is an exercise that is using this, show this. Okay, it's pretty easy. You just have to go from position to momentum basis. And how do you do that? Fourier transformations. Okay, it got stuck again. Like, give me 1 second. Got stuck. Sorry, I think there is some sort of a bug with this version of journal. Okay, so now what we're going to do, we're going to, let's call this equation A. I can never track my equation numbering. Sorry about that. Let's call this equation A, and let's see how we can get rid of this piece. Okay. So to do that, what we're going to do, we initially have this v of q. This was what, delta t. There was this q of r plus 1. We have this e to the power I p squared 2m. This is an operator. We have this delta t, and now we invoke the identity on the momentum basis. So this is dp by 2 pi. Let's say this is p, this is p, and this is say q of r. And again, now you can expand this exponential, this e to the power minus I p squared by 2m, and you can use the relation that p acting on the momentum eigenvectors will just give you the momentum eigenvalues. This is another eigenvalue relation in quantum mechanics, pretty standard. If you do that, you can pull this guy out as well, outside the exponential. Okay, so on the next line you have I v of q delta t e to the power negative I p squared 2m, and now you have this dp by 2 pi. You have this q of r plus 1. You have this p. You have this p, and you have this q of r. Something like this. Okay. Am I right, or did I make a mistake? What do you guys think? Did I make a mistake?
Delta plus delta p. Do you know that? P squared over.
Oh, yes. The delta t is yes. Yes, you are right. So in this case, it looks pretty easy. There is another relation you can use.
আচ্ছা পিটা কেন বাইর করতে পারলাম, লাইক আমরা তো এখানে পি এর সাপেক্ষে একটা ইন্টিগ্রেশন নিতেছি, সো
Oh yeah, sorry. The integral sign should be, yeah. It should be over there. Yeah, you're right. We're integrating with respect to p. Yeah, sorry about that. That was a major mistake. Thanks. So now you need to use another relation, and this will be an exercise as well. I think Nahi once asked me to do it, like, I don't know, maybe a year back. Um, and that relation is something like this: q prime is equals to e to the power I p q prime. And if you consider some q prime of p, this is just the complex conjugate of the what you did, this guy. These are exercises as well, or maybe it will be in the homework, you know. Do you guys know these relations, or have you any of you ever tried these things?
No, this is my first time seeing this actually.
Oh, okay. Oh, okay, fine. Don't worry, I'll guide you. Maybe it will be in the homework problem, okay? Because you
Yeah, I
have to
actually want
write
to
down
know.
the, yeah,
Yeah.
okay. So the hint is something like this for doing this. You have to start from either here or here. Okay. First, you have to start from here. Then you have to do something that will let you construct these things. And then to get the exponentials, you have to, you know, choose a specific representation of the operators. But I won't tell you which representation, because it will depend on which space you want to work on. So you start from here, okay? That's
Yeah,
the
it's my
idea.
first. This is my first time seeing the relationship, but like I think I can solve this one.
Yeah. Okay. If you start from the eigenvalue equation, it's pretty easy.
Hmm.
Okay. So let's try to invoke these relations over this equation, okay? And I think I should mention one thing, that maybe in the notes I didn't, did all these calculations because it would become huge. So that's why I didn't do it. If you want, I can make a PDF of this and give it to you guys after the class. P squared 2m delta t. So q inner product with p should be a plus. I always forget these things. So this guy should be a plus. E to the power I, and it is what, q of r plus 1 inner product with p, right? So we have p q of r plus 1, and this guy should generate e to the power minus I p q of r, right? So if I combine this guy and this guy together, actually what I should get is something like this, q of r, right? Oh, and I think maybe I missed it. Did I miss something like a delta t or something like that? I don't know. Let me check. Nope, I didn't miss anything. Okay, that's fine. Oh, so tell me, how many of you know how to evaluate Gaussian integrals? You guys do know how to evaluate Gaussian integrals, okay?
Yeah, more or less.
Not in the
Yeah,
complex case.
yeah. I'll
Yeah.
show how to get rid of that thing as well. You can evaluate this kind of things, right? From minus infinity to plus infinity or something like that. Because try to think of the momentum values. They run from what? 0 to infinity, right? If you consider the magnitude of it.
Hmm.
And the position space, it runs from minus infinity to plus infinity. So the
Yep.
Gaussian integral is defined for, both of these cases, right? So we can try to evaluate this thing, right? And the case we have over here is similar to this one, apart from the fact that there is no c is 0. So this is a Gaussian integral. To complete the square, you can do the following. Completing the square, you can try the following substitution, um, or you can even try to figure that out by yourself. Uh, the substitution goes like this: p prime is equals to p minus m q minus q prime divided by your delta t. Okay, is that clear, everybody? Instead of q prime, you can write q of r plus 1. Instead of q, you can write q of r. Okay, so it's just a matter of notation. And if you do that, the first thing that Nahi mentioned, oh, we have some, e to the power minus I and something like that. So That's a little bit troublesome. And if you want to do it blindly, you might say, oh, I have some I, but I is a constant. I'm not considering the fact that these are actually uh, very highly oscillating integrals and stuff, so they may not converge. If you don't want to consider that, then you should end up with so this is not a non-formal way. The non-formal way is that after you try the substitution, your integral will look something like this: e to the power I m q minus q prime whole square by 2t, I mean 2 delta t, whatever. Then you have this dp prime 2 pi e to the power negative I p prime squared by 2m delta t. And again, you are not considering, this exponential, highly oscillating integrals and stuff. So you can write this as e to the power I m q minus q prime squared 2 delta t, and you do this integral and you write it as m divided by 2 pi I delta t. You can do that, but it's not, it's just not right. That's a fact. We shouldn't do that because these are highly oscillating integrals, so they may diverge as well. So there are two ways to do this. Both of them are like essentially same. um, I think Rakin asked me to show this to you guys, so that I think something he will show in his course that will be relevant to it. There's a thing called Week's theorem or Week's rotation. Not Week's theorem, we call it the Week's rotation or weak rotation. This is a common technique that you will encounter in quantum field theory, because most of the integrals that we encounter there comes with e to the power some negative I 10 times something, some variable and stuff like that. So this type of integrals are in general not convergent. To make them convergent, what people do is that in these integrals, they take this it to some tau. And how does this look on a physical ground? Let's say you have this time axis over here, right? And multiplying with I, what does that mean? Whatever you had, you are now rotating it on the anti-clockwise direction by 90 degrees, right? Did everyone do complex variable?
No.
Okay,
I
so
think
think of it like this, okay? So when you are multiplying something with -1, what does that mean? For example, -1 times 5. This gives you -5. So on the real line, you're starting on 5. You are multiplying this with -1, which is simply I squared, right? So you're getting rotated 180 degrees.
Mm.
I know.
Yeah.
So when you multiply with I, that will just, take you, and it will just drop you in somewhere in the middle.
Oh, I see. Yeah.
Okay, so this
Yeah.
is like a rotation.
Mhm.
So this is called the real time. This t, people call it the real time, the time you usually deal with, and this is called the imaginary time. And a lot of interesting results come out of this. If you study general relativity, there is a notion of distance can be positive, negative, or zero, even in special relativity, right? If you have studied special relativity, you have seen that your metric is something like this. But if you consider a weak rotation, you can get rid of this minus sign over here and make the metric completely Euclidean. So that's why some people call it Euclidean time as well. Yeah. Even let me show you another funny thing. You guys know that the time evolution operator in quantum mechanics looks something like this, right?
Yeah.
Now, instead of it, let's substitute this with tau. What you have, e to the power h tau. This reminds you of something regarding statistical mechanics? Does this
Oh
remind you?
yeah, it looks like
It looks like a partition function.
yeah, it does.
Yeah, exactly. So yeah, this is a very interesting thing. Okay, so you can do this on this integral over here that we are discussing. instead of delta t, you can take some Euclidean time, okay, and it's fine. You can then you have a convergent integral, right? Take this I, take this delta t, replace this with some delta tau. You have it. You have your convergent integral. No harm is done.
But are we sure that the value of it hasn't changed?
Yeah, value the value won't change. I mean, the only thing you have to do at the end of your calculation, if you want to see your results in real time, you just have to put back the substitution again.
I mean, what I'm saying is that since you turned a divergent integral into a convergent integral, how do we know the value of it hasn't changed?
Well, in general, they're not divergent, right? If you consider I to be like, if you are someone like who really doesn't care about J, okay, these exponentials, they have these sines and cosines, it's highly oscillating. And there is another kind of interpretation when you considering these highly oscillating integrals. The further you go away from the origin or the point of interest that you're doing your analysis with, they should die out. All the oscillations should cancel each other out. They can do that, right? This is like a destructive interference.
Yeah.
The result won't change. No. Yeah, the result won't change. I mean, QFT is all about dealing with these divergent integrals. The first integral you will ever encounter in QFT, the instructor will tell you, oh, this is divergent. But let's introduce some counter terms and try to do it, and then you will see some really nice finite results coming out of those divergences. Now, whether
Like the
those
sum of the sum of all the positive integers being negative 1 over 12.
that's a zeta function regularization. Yeah, that's a regularization as well. Yeah, people can regularize. Like, you can choose two paths. You can be adamant about these integrals being divergent, or you can be a little bit open-minded and manipulate some stuff to see what you can extract out of those divergent integrals, right? Yeah, I think I just insulted mathematicians, whatever, that they're not open-minded. I need to cut these things out from the video. Can I see like what timestamp this is? I need to cut them out. 6:04. So that's like precisely 1 hour later. Okay. And please, okay, let's forget this stuff. Okay. So this is the weak rotation thing. Now you know weak rotation. You can show your friends some magic tricks with weak rotation and stuff. So I think we are all clear on the fact that how we are going to do all these integrals, right? It's a bit messy over here. But do you understand how did I do the thing that, extracting out these p's? How did I transit it from the operator expressions to irregular canonical variables?
Kind of. That's the answer I have.
Okay.
I'll have to go through this again to
Okay, that's fine. So don't worry about it. In the homework, maybe I still haven't finished typing your homework. So in the homework, I'm gonna make you derive all these things step by step. So even if this writing is a little bit messy, don't worry about it. But the main thing is what I'm doing here. That, like, for this, when I take this example, okay, you had this hat over here. I'm just getting rid of the hats. I don't want to deal with operators. I want to deal with something that's manageable. Okay. So this thing can be again written as 1 plus e to the power, sorry, not e to the power, some p squared. There is some garbage over here, e to the power 4, yada yada yada, and they're acting on some p vector, right? And we're using the eigenvalue relation. So that's how we did it. That's the summary of it. You know eigenvalue equation, you can do it. Is that clear, Shutosh? Okay. Now that we know that what we're going to do or how to evaluate these integrals, let me write down the expression for the kernel again. Okay. But this time I'm going to use all the results I derived so far. that means the result over here. And as I said, okay, you are turning your divergent integral into a convergent one. Now, are you sure the result is not changed? Well, the result doesn't change. The only thing is, instead of I delta t, you are writing it as del tau. But after the calculation, you are putting back this I and t's again, because we are, dealing with our real time and stuff like that. So I'm going to write the kernel again, the thing that we initially started with. And that expression was what? R equals to 1 to n dq r plus 1. Sorry, this should not be a bracket, it should be a bra. There should be dq of r. There should be e to the power negative I Hamiltonian t of r plus 1 minus t of r, q of r, q of 1, e to the power negative I h t of 1. And we wrote it as delta t's, right? Instead of t of r, all these delta t's and stuff. So something like this. And after all the things that we did, the mumbo jumbo clever algebra, or so to say the tedious algebras, we can finally get rid of all the operators that we had, and we can finally write our result for any individual q of r plus 1 e to the power minus h delta t of q of r as square root over n 2 pi I delta t e to the power I 1/2 of m. You have q r plus 1 minus q of r delta t whole squared. This is squared, and there is another delta t over here. You can obviously keep only one delta t. I just wrote it for the reference that, when you write your kinetic energy, that is usually what, 1/2 of mv square, right? And v is just what, q dot. Q dot means dq by dt. On that analogy, I can keep this, or you can skip it totally. And the reason I'm keeping this will be evident very soon. Minus I d of q of r, and there is not much space left. There is a delta t as well. So this is the thing that we started with. This guy, we started with this, the expression for the kernel. Then we took out, since all the expressions are something like this, similar to this guy over here, that's why we evaluated these things, right? And now what do we have? We have a product in front, right? And there is another term like this that is similar to this one, just you put r equals to 0, then you have the last term on the kernel, right? And this is the same result. So the kernel has these two parts, this guy and this guy. So the first part, let's say this is the first part and this is the second part. Let's say this is equation B. From B, or the results of B, the first part should yield the following. You have n products, like r is equals to 1 from 1 to n, the values of r, like, so there are n things right there. So you have square root over m 2 pi I delta t to the power n, right? And you have some exponentials like this, but they're all products. So if you have e to the power, let's say I equals to 1 to n xi, you can write it as summation over xi, right? This is something you guys know. So using this fact, what I can do right now is that I can write it as e to the power sum over sum r equals to 1 to n I 1/2 m q of r plus 1 minus q of r whole squared delta t squared delta t minus I v of q of r. And the second part will similarly yield the same result, but this time one of the r is 0 and the r plus 1 would yield a q1. So this is just one term, m turns to phi I delta t e to the power I 1/2 m q of 1 minus q of 0 delta t squared delta t minus I v of q of 0. Already? Is this okay with everybody?
Yeah.
Yeah, I get it.
Okay.
Kind of.
And now you just multiply these two parts, right? To get the full expression for the kernel. Right? Yeah, just look at the expression of the kernel. You have this first part and the second part. You just need to multiply them together. And I think
Then you need another integral sign, right?
আচ্ছা v এর সাথে কি এখন আর কোনো ডেল্টা টি মাল্টিপ্লাইড নাই? Sure না।
where? Yeah, there should be a delta t. Sorry, I keep forgetting the delta t's. Just give me a reminder. Oh, you are forgetting time, you know. Yeah. So you just multiply them. That's it. I think, did I miss a integral measure on the expression for the kernel? Nope. Did I? I think so. No, I didn't. Yeah. Okay, that's good. So now you need to multiply these two parts. Yeah, Sujash.
Was there supposed to be like a square on q1 minus q
Oh, yeah.
naught?
Yeah,
Okay.
there should be a square. Okay, now you are multiplying these two very beautiful equations. Let's say some I, let's say some j. So you are multiplying this I dot j to write down the expression for the beautiful kernel that you are dealing with. If you multiply, this is just what? M divided by 2 pi I delta t square root of this thing n plus 1, right? And if you want to write it as 1 n plus 1 by 2, that's fine as well. And if you multiply these two guys, all you need to do is to just change the summation indices. Instead of starting from r equals to 1, you can now start from r equals to 0. So e to the power summation over r equals to 0 to n I times 1/2 m q1 minus q, sorry, not q1. I should write q of r plus 1 to 0 whole square delta t squared delta t minus I v of q of r delta t, right? Now we are dealing with a space where, you know, time and q, all of them are continuous, right? And what did we say earlier? That our time steps should be broken into very, very small pieces, like very small time steps, like the time from 0 to capital T is being broken down into really small steps. So at the end of the day, if you write capital T is equals to some n times delta t, this will mean that delta t would be equals to t by n, where n would be the number of steps or time steps, and you want to make this delta t as small as possible. So that means delta t would be going to what? 0. So that means when you take this delta t goes to 0, on your summation over the exponential, this guy will turn into something. And I think this is something you all know. The summation will go to the integration, right? Is that like
But there's no
Clear, right?
limit in front of the in front of the sum, right?
no, we are just taking it.
Oh,
Like Yeah, at first we do some discrete,
I
you
mean,
know,
the delta t can act as the time integral measure now,
Oh,
maybe.
right. Yeah.
So I think we get some sort of action, isn't it? I'm
yeah,
guessing. Yeah.
yeah, that's the action
Right.
for a single particle. So let me write it down again for the reference. So uh, when we take this limit, this r equals to 0 to n of this quantity m by 2 q of r plus 1 minus q of r. Now you see why I wrote delta t square in the denominator instead of writing a delta t. Minus v of q of r of delta t. When we take this guy, that means when you take the limit delta t goes to 0, it's just this dt, 1/2 of m, you know, this dq by dt squared minus some v of q. And this is what? dt times the Lagrangian or the Lagrangian density, whatever, q dot. This is just your action, right? So we are almost done, but there is a little bit, trouble in taking delta t goes to 0. Look at this guy. There is a delta t in the denominator, right?
Yeah.
So what do you guys think? Yeah, like this is gonna blow up, right? That's what it looks like. But yeah, this is where we turn into a little physicist or something. Is that we are simply gonna call it a integration measure. Like this sounds pretty absurd at first, uh, but we are not going to worry about it right now. In fact, uh, that should be done in an advanced quantum field theory course. But let me try to give you some point that I'm trying to make. Instead of that whole thing, that square root over m divided by 2 pi I delta t to the power n minus n plus 1, let's write it like this. Delta t starts from r equals to 1 to n, and this is the factor you had, right? The factor we have so far, right? But did you guys notice that I wrote it as the kernel, but the kernel had another integration measure over here, some dqr?
Yeah.
Okay, so if you put that over there, this dqr, the missing piece, you can take this guy with dqr and call it, oh, when this delta t is going to 0, instead of the ordinary measure where these q's are just some coordinates, we get a functional measure. How to write this d in a cooler manner. Yeah, that's one way to justify it. And they can be given the expression over here, it can be given some really precise meaning, but again, if I try to cover that, um, it would take a very long time. So for now, except that when you take this delta t goes to 0, you can replace your ordinary measures with a functional measure. And in fact, in the notes I used this notation so that you guys understand clearly that this is a functional measure. So putting all this together, after all the hard work, we have the expression for the kernel, or so to say, the transition amplitude. You guys do understand this transition amplitude and the kernel, they're the same thing, right? Just play with the brackets.
Okay.
So this is your path integral. This is the thing that we have been looking for. In fact, they're also written as some z of z, but for that you need to have some source as well. So this is the quantity of interest, and look how this plays in. The action is a classical thing, right? With all the classical variables. But the kernel itself, if you look from this perspective, it's what an operator expression. So this is the genius of Feynman. Like, this guy invented this method that takes in, your classical variables and spits out something quantum, or that has an operator expression and stuff like that. So why is this quantity of interest? Well, in quantum field theory, unlike in quantum mechanics, you are not interested in something like a wave function. You are more interested in something called a correlation function. And the most general thing that you can write for a quantum field theory is this guy, this path integral functional, like this. But instead of q, let's use phi so that you understand this is from quantum field theory. And you would have an action that consists of the fields and some source. And from this thing, you can figure out each and every interesting quantity. In quantum field theory, for say, let's say you are interested in some 4-point functions like this that consists a loop. You might consider a graph like this. This is called a 4-point correlation function. I'm not going to explain what are these. Maybe someday else, or maybe in another course, but not in this course. All these lines, they represent something called a propagator. And what the propagator does is that it, let's say you had some particle over here. It's going from place A to place B. Another particle is on C. It's going on D. And at these 2 points, they exchange something in between. That means they interact and stuff like that. A lot of things can happen. Okay. So those are the things that are of interest in quantum field theory, and you can get your whole thing from this guy as well. And even in quantum mechanics, like you can get your wave functions and all the results that you get from your standard canonical quantization procedure. You can even get that from this procedure as well. And a nice example is the harmonic oscillator, and that will be on your homework. So what I want to show you in this lecture is just 2 very special cases for quantum field theory. First is the Klein-Gordon theory, the free scalar field, and the second is the Dirac field. But don't worry about it if you haven't heard of this before. This is just me discussing some applications of the functional calculus that we saw earlier in physics. Okay. Even if you don't understand the physical meaning of it, don't worry about it right now, because first you need to get a quantum field theory course. So okay, so just before I continue, any questions, anyone?
আচ্ছা, so could you like scroll up and ওই যে উপরের দিকে একটা ক্যালকুলেশনের কনফার্ম ছিল।
কোনটা?
So আমরা যে বেসিক্যালি ব্র্যাকেট এক্সপানশনটা শুরু করছিলাম ওই ফাংশনতে psi of qt ওই জায়গা থেকে। So হ্যাঁ, এখানে রাইট। সো বেসিক্যালি এখানে একটা ব্রা আসে হচ্ছে কিউ r+1 এর একটা করেসপন্ডিং ব্রা আছে একটু নিচে। এখন ওটার তো কোনো কেট পাইতেছি না, সো লাইক আই এম গেটিং কনফিউজ, ওটার কেটটা কই যাবে? r+1 এর করেসপন্ডিং কেটটা কই? লাইক
ওকে, why would there be a corresponding ket for r+1? What do you think that? Because you are starting from q equals to 0, let's say, and you want to go to this q of r+1 point, right? So first you write the Schrodinger equation, then you sandwich that Schrodinger equation with the q of r+1 bra, right? So that's why there is no corresponding ket of q of r+1. Do you get it now? Like, this is the
ও
finishing
মানে
state.
এটা হচ্ছে ডিসক্রিটাইজেশন করার ফল হয়েছে
Yeah,
নাকি?
this is the last, your last stand. Like this is your
আচ্ছা
end point. This is where the journey ends, Arki. Yeah.
আচ্ছা আচ্ছা, এখানে একটা কনফিউশন হচ্ছে, লাইক এখানে লাইক আমরা যে এরকম লাইক কিউ নট এর একটা ব্রা, তারপর কিউ ওয়ান এর একটা ব্রা, তারপরে সরি কেটস বা হোয়াট এভার, লাইক প্রতিটা টাইমের ইটাকে যে ভাগ করতেছি, ওই প্রতিটা টাইমের জন্যই কি আমরা এরকম একটা অ্যাসোসিয়েটেড ব্র্যাকেট নিতেছি এই পয়েন্টার অপারেটরে? সো
এই যে গ্রাফটা দেখো, this graph over here. Where was it?
সো তার মানে কি লাইক মোমেন্ট, সরি পজিশন অপারেটরটা টাইমের সাথে সাথে চেঞ্জ হইতেছে, যেহেতু এটার আইগেন কেটস গুলো বা আইগেন ব্রাস গুলো চেঞ্জ হইতেছে এরকম লাইক?
No. You are doing quantum mechanics, right? And you want to move from point A to point B. So can you say that at time t equals to, let's say, t of 5, the particle was at q of 5? No, you cannot say that. You can associate a probability, right? You get my point, what I'm trying to say? You are considering a time evolution of the particle.
আচ্ছা, মানে আইগেন স্টেজ গুলো টাইম এভলিউশন হইতেছে, ইজ ইট লাইক?
I don't know, I'm a bit confused, like what you're trying to say. I don't get it properly.
আচ্ছা
What I'm trying to say is that the particle is moving through space and time. Time is acting as a parameter, right? And we are seeing the particle, the particle could be anywhere. All we know for sure is that it's starting from some reference and it's going on, some q of r plus 1 or some q of f. In between, the particle be at any place, because this is just one of the paths, right? And when we take those limits, then we, sum over all the paths. You get my point? Because look at this summation on the exponential at the very end. Oh no, it's stuck again. What the heck is wrong with this? Yeah, where was it? Yeah. So just look at this summation. Even if you look at these summations, well, it's taking all the possible paths, right? From q0 to qf or q of r plus 1, and then it's acting as a weight over the exponential. So what I think you are trying to say is that, are we thinking that the position operator, is it changing with time? Well, I don't think so, because that would further complicate things when you try to expand the exponential and use the eigenvalue relation, because then your position operator would be time dependent, and if your position operator is time dependent and it's acting on some q, I don't know. I don't think of it like that way. What I think is that you're moving from one point to another. In between, at every point, you can associate some probability, right? So there should be no confusion about that. Yeah.
আচ্ছা, এইটা কি ইয়েতে থাকবে হোমওয়ার্কে, এই ক্যালকুলেশনটা লাইক আজকে যেটা করছিলাম?
Maybe. I haven't decided yet.
আচ্ছা, সো অ্যানাদার থিং, লাইক এখানে তো আমরা যে ফাইনালি যে রেজাল্টটা পাইলাম, ঠিক কোথায় আমরা বলতেছি লাইক ইট ওয়্যার সামিং ওভার অল দ্য পাথস, দেখ এখানে তো আমরা একটা স্পেসিফিক পাথ নিছি, ওখানে তারপরে কিউজ গুলোকে ভাগ করে নিছি, সামটা তো একটা স্পেসিফিক পাথের জন্য হচ্ছে। সো লাইক,
do you see this functional measure or this guy?
আচ্ছা, হ্যাঁ,
okay,
বলি, আচ্ছা, oh I see.
Now do you see what's happening?
Yeah,
this was your q axis, right? And this was the final point, and this was the time and something like that. So you are going from this to this with all the paths and stuff, and this is just your weight. With all paths, there is a certain weight. So from here you can also see that the classical paths dominate the integral as well.
Acha.
Okay.
Okay.
So this is the guy that tells you are summing over all the paths, and this is the guy that is a weight. That's why they're called path integrals, and they're at the end of the day just some functional integrals. Okay.
Okay.
Okay. So